Hi, welcome to our recent work, Piecing ULET, learn to jointly reconstruct and segment the cardiac walls in 3D from CT data. We all know that heart disease is the major cause of human death all over the world, and the function of left ventricle is of great interest of the radiologists and cardiologists. Also, the shape of the LVMLO plays an important role in diagnosis of cardiac disease and in surgical and other invasive cardiac procedures. In traditional methods, we can first image the heart by some scanners and then do cardiac segmentation. Based on the segmentation masks, we can build a mesh. For a mesh, it has two parts. The first part is a set of vertices, and the second part is a set of key edges, with each connecting two vertices. The set of the vertices will form a point cloud, and each vertex V in this point cloud has a 3D coordinate x, y, and z. The mesh is a description of the 3D shape of an object. The point cloud is also a sparse representation of the 3D shape. For the cardiac segmentation on CT images, ULET-based fully convolutional neural networks are sort of the state-of-the-art methods, but there could be some problems. For example, the apex part is very thin. If the segmentation is not accurate, there could be some holes on the reconstructed 3D shape. For the point cloud prediction from images, the recent point outlet can predict a point cloud of the right ventricle from a single 2D image. But we should notice that such a single 2D image cannot provide all the information that is needed to predict an accurate point cloud. Inspired by the previous works, we designed this ULET model. It has three parts: image encoder, point net, and mask decoder. The input is 3D volumetric image, and the image encoder can extract contextual image features from the input images and directly predict a point cloud. The point net will extract point features from the predicted point cloud. Combined with the contextual image features and the point features, we use the mask decoder to reconstruct the segmentation masks. Our PC-ULET model is some kind of similar as the ULET model. The difference is that we let the output of the encoder be the point cloud. This point cloud can provide an explicit shapewire for the segmentation task. So, with such an shapewire, we can expect more accurate segmentation masks. For loss functions, we use the chamfer loss to supervise the prediction of point cloud, and for the segmentation task, we use the soft dice loss. This PC-ULET model was trained end-to-end by this VTL loss. We evaluated our model on the STACOM 2017 challenge dataset. It's a 3D cardiac CT dataset which contains 20 subjects. We used elastic deformation to augment the dataset by 200 times. Here is the process of getting the ground truth point cloud. We downsampled the point cloud by a number of 4096. We performed four-fold cross-validation experiments. Here are some experimental results. We have two tasks. For the PC reconstruction task, we use chamfer distance error to evaluate the results. We compared our method with the point outlet. The input could be a single slice image with volumetric images. The convolutional could be 2D or 3D. For the segmentation task, we use the dice coefficient and host of distance error to evaluate the results. We compared our model with the ULAT model. From this table, we can see that our PC-ULAT model achieves the best performance on both the PC reconstruction task and the segmentation task. Here are some video examples. We can see from column A that the point outlet cannot reconstruct the points on the atrioventricular wing part and the apex part. However, our PC-ULAT model reconstructs the points on such regions successfully. For the segmentation task, the ULAT model could make some mistakes. So there are some holes and isolated outliers on the reconstructed 3D shape. But our PC-ULAT model can predict a complete and accurate point cloud without any holes on it. We also did an ablation study to explore the effect of joint learning and skip connections. Here, we tested 3 models. The first model is the PC mask decoder. It has the point net part and the mask decoder. The input is the point cloud, and the output is the segmentation masks. With this model, we want to show that convolutional neural networks can reversely reconstruct dense segmentation masks from a sparse point cloud. We can see from column B that the predicted segmentation masks are dense, and they are surprisingly very close to the ground truth. The second model is PC-ULAT no skip. There is no skip connections between encoder and decoder, so it cannot utilize the contextual image features. From column C, we can see that the predicted segmentation masks are very coarse. In contrast, our PC-ULAT model can recover most details of the segmentation masks by using joint learning and skip connections. To conclude, our PC-ULAT model can jointly learn to reconstruct the 3D point cloud of the LV-MAO and obtain the segmentation masks. Our PC-ULAT models the shape of the MAO directly from 3D volumetric images, which is accurate and avoids errors due to inaccurate segmentations in the traditional methods. Our PC-ULAT can utilize an explicit shape prior provided by the point cloud for more accurate segmentation results. For the first time, we show that convolutional neural networks can reversely reconstruct dense masks from a sparse point cloud. That's it. Thank you very much for your attention.